When you look at a modern device from the outside, it can seem like a solid, silent block of magic. You press a button and things just happen. But if you lift the lid and peer inside, you'll find a highly structured, hidden world. The inside of your computer operates like a bustling, incredibly organized metropolis. It has its own architecture, flow of traffic, and zoning laws. Every city needs a layout, and in your computer, that is the motherboard. It acts as the concrete foundation and the main city grid. It's the large, flat circuit board that physically holds every piece of the system together in one place. And sitting right in the middle of that grid is the CPU, or Central Processing Unit. Think of this chip as the central city hall. This is where all the primary processing, calculating, and big decision-making actually occurs. But there is a catch. A powerful city hall is completely useless if its decisions can't quickly reach the rest of the city's resources. So, how exactly does a specific instruction generated at City Hall travel out to be stored in the memory archives or drawn onto your display screen? Physical cities use asphalt roads to move traffic. Computer architecture relies on highly organized, conductive pathways known as buses. While the word might make you picture a yellow vehicle taking kids to school, in electronics, a bus is simply a physical, wired route that shuttles electrical data from one point to another. This road layout allows the city to coordinate millions of tasks simultaneously without descending into a massive pileup. This schematic lays out a strict hierarchy of computer roads. Surrounding the CPU is the blazing fast cache bus for urgent data. Further out, the memory bus highway handles high-volume traffic to main memory. Finally, backplane routes like the PCI bus connect external hardware. This tiered road hierarchy is put in place for one specific reason. It ensures critical CPU calculations are never delayed by slower traffic arriving from distant parts of the system. But having different road speeds creates a logistical problem. What happens when extremely fast highway data meets slower interstate traffic? To prevent collisions, the system uses architectural bridges, like the I/O bridge for input and output. These function as massive roundabouts that safely merge fast and slow data streams. If we zoom out to the outer edges of the city, we find the external ports, like USB and FireWire connections. This diagram shows how ports operate as shipping docks. Notice how a USB hub acts as a distribution center, organizing multiple external devices to share a single highway lane into the city. Without these bridges and shipping docks, any new information plugged into your computer could never safely integrate into the central processing flow. Let's put all of this together and trace a single everyday action. Imagine you simply click your mouse to open a program. The moment you click, a digital signal enters the USB shipping dock and merges onto the backplane routes. That data packet navigates the I/O bridge, waiting for the proper clearance to move on to the faster inner highways. It makes a final lightning-fast sprint up the local cache bus and arrives at the CPU, where the instruction is processed. Almost instantly, the CPU sends the visual update back down through the bus hierarchy, out to the graphics card, so your screen can reflect what you just clicked. That entire cross-city commute, the data processing at City Hall, and the return trip to your screen happens entirely within a fraction of a single millisecond. This brings us to a common misconception. People often assume that buying the fastest possible CPU guarantees a blazing fast computer. But if your motherboard has narrow roads and slow buses, you create a bottleneck. The smartest city hall in the world can't do its job if it spends most of its time just waiting for data to arrive. So the next time you boot up a game or plug in an external drive, picture that hidden, roaring metropolis of traffic right beneath your keyboard. Performance relies on the efficiency of the city's communications, just as much as the raw thinking speed at City Hall.